Sure. Can you hear me? Yeah.
Yeah.
Yeah, perfect. So yeah, thank you very much for this kind introduction and for the invitation. So today it is my pleasure to talk about some of my work, which is entitled Horndeski and the Sirens. This is ongoing work together with my PhD advisor, Lucas Lombreezer, who is here attached to the mast, and with Pierre Fleury, who is in Madrid. And these are based on these three references down here. And at the end of the talk, I'm also going to talk a little bit about some more recent work, which is unpublished, together with Julia Cousin, who is in Geneva, and Macarena Lagos, who is at Columbia at the moment. And so you may see this very fancy background and wonder what it is. And so this is inspiration from Odysseus in the Sirens. So Odysseus is it's the story from Greek mythology, and Odysseus is here interpreted by Lucas, who is attached to the mast. And the reason for this is because there are these sirens who have this very charming voice, and they're half birds and half women, and they charm the sailsmen to come to their island, and then they eat them. So it's a bit frightening. And so Pierre and I, we have some wax in our ears so that we cannot listen to the charming chant, but we are rowing. Lucas, he's attached to the mast so that he cannot be tempted to go to the island, but he has his ears free so that he can listen to the very charming song of the siren. So that's a metaphor, and it's up to you to see how far we can take it. So perhaps just a little bit of an introduction for myself before I dig in. I start my talk. So I've been working mostly in gravitational wave physics so far. I also have some interest in foundations of gravity. I'm starting to get interested in relativistic effects, working on a project with Camille Bonvin in Geneva about the cosmic dipole mismatch. I also have some interest in H-naught tension, and in the future I hope to work also on inflation and primordial black holes. I think those are very exciting topics. And here in the background, that's a bit where I come from. It's also EPFL, where I also partly studied. And my house is somewhere over there. That's the La Clément, which is very beautiful. Yeah, I just wanted to say that. So the outline of my talk, I'm actually going to spend quite some time talking about some motivation and giving the context of my research. This, I think, will be especially interesting to PhD students and perhaps postdocs which are not in the field of gravitational waves and scalar tensor theories, perhaps. Then I will talk about gravitational wave propagation in those scalar tensor theories, which are an alternative theory of gravity. And in the second part, I will talk about this more recent work, which are about degeneracies with GR-length gravitational waves. Finally, I will give my conclusions. So the why, the motivation, of course, you have all seen this plot, is that we want to challenge GR. So I personally prefer this one, which is the same, but it's my version. If you trust GR, well, you have to introduce these very strange components of the universe, which you call dark energy, dark matter, which we do not observe at CERN. We have this dark energy. It's a huge part of the energy budget in the universe. We don't really know what it is. And the least we can do is to ask, can we really trust this theory of gravity on large scales? I'm not saying that we're solving the cosmological constant problem. I'm just saying that we should challenge it. And so I always try to focus on the largest piece of cheese, which is this one. So it's alternatives to general relativity in order to explain dark energy. So if you want to go beyond general relativity, well, you first have to realize that GR is a very unique theory. This was shown by this mathematician in the 1970s. He realized that if you want to write down an equation of motion for the metric, which depends on the first and second derivatives of it, and you want to introduce some notion of covariant conservation of energy, so that the left-hand side is divergence-free, The most general thing you can write down is this Einstein tensor and in linear combination with just the metric itself. And that's just GR. And it's the most general thing you can do. And if you want to go beyond that, you should break one of the building assumptions. And this is known as Lovelock Theorem. So you have one of these four possibilities. Of course, you could believe that gravity is not a metric theory. You could go even beyond. If you trust that gravity should be some metric theory, then you have one of these four options. So you can break Lorentz invariance. You can put some indices around here. You can, but of course, then you have to worry about causality. You can also change the number of space-time dimensions. So you can change this number here. You can add new degrees of freedom, and this is, the most popular thing because you have this standard model of particle physics, which contains scalars, spinor fields, vector fields in the form of bosons, all of these fields. And of course, why not just add one and perhaps couple it to the metric? And every time you will see a blue box like this is because I want you a bit to focus on that part. So that's the part on which I'm going to focus. Another possibility is to abandon locality. And of course, implicitly, all these interaction terms, they depend just on the x position. But you could imagine that you have interactions at a distance. And this, for example, is studied by people like Michele Maggiore in Geneva. So the equivalent of GR for scalar tensor theories, if you add an extra degree of freedom, is called Horndeski theory. And so Horndeski theory is you also have a matter Lagrangian which does not depend on the scalar field, which is this phi. You have the Planck mass, which is the inverse of 8 pi g Newton. And then you have these four pieces of Lagrangian densities, which depend on the scalar field, is kinetic term and the metric tensor. And it's given in terms of these free functions, G2, G3, G4, and G5. And if you choose them in a specific way, you can describe any theory you want, not any theory, any scalar tensor theory you want. So for example, if you set G4 to 1, that's just the Einstein-Hilbert action is GR. You can set G2 to minus 2 lambda so that you have a cosmological constant. But you also can have an arbitrary potential here. So you have quintessence, k-essence, the Galileans, and these terms, which are very fancy and give you very fancy phenomenology. And here, again, I want to focus on this blue box here, which is roughly, it multiplies the Planck mass, so it multiplies the Newton constant, if you want. And this, it means that you have roughly a scalar field-dependent Newton constant. So if the Newton constant depends on the scalar field, and the scalar field can depend on space-time, that means that you have a Newton constant which can depend on space-time. And this theory was discovered in 1970s by Gregory Horndeski, and he was not very successful. His work was very unnoticed, and he quit physics and became a painter. And he came back to physics in 2010 after his theories were rediscovered. And then a lot of people started working on the Horndeski theory, and he said things like, nobody's going beyond the Horndeski without me. And when we asked him if he would agree for us to write our title Horndeski and the Sirens, he replied, yeah, sure, no problem. Has anyone seen my recent paper, or does it need to languish for another 40 years in obscurity? You should not forget to follow his work, because this guy has 40 years of advance on the rest of the community. So, of course, if you want to modify GR, GR is very well tested. There are many tests of GR. One of them, for example, is the lunar laser ranging test. So it's a test of the force between the Earth and the Moon. You send some laser to the Moon, it reflects on the Apollo mirrors, it comes back, you measure the time of flight. If you're smart enough, you can put a constraint on what is the effective Newton constant you have here. And you can see that it varies very little, less than one part in the age of the universe, right? So it doesn't vary a lot. And then you have another independent test which depends on how relativistic particles travel through space-time. And for example, some photons can be emitted by this Cassini spacecraft, which was sent to study Saturn. And you can put a constraint on this gamma, which in GR is 1, and you see that the tests, the constraint that we have on this gamma is that it should be really close to 1. And so that tells you that if you want to build a model, a scalar tensor theory, you have to satisfy these predictions. And these predictions tell you that, GR is very, very close, extremely close. Well, gravity is extremely close to GR. So perhaps I just want to mention an ultimate test, because we're talking about gravitational waves. You have this Hulse-Taylor binary, which is a binary system. As it emits gravitational waves, it loses energy, and the period is shifting. And you can this was measured since the 70s as these red dots. And this blue curve is not a fit, it's a prediction of GR. So that tells you that we know extremely well how energy is lost in the form of gravitational waves, at least for this Hulse-Taylor binary. And at this point, you might wonder, oh, then, scalar tensor theories, forget about it. The constraints are so tight, you never can explain anything with this kind of theories. But there is a caveat, and the caveat is called screening. So screening, what is this? It is the local recovery of GR in high-density environments. So for example, all these, well, not all, but most of these experiments, they're performed in high-density environments such as the solar system, galaxies. They're not performed in voids, for example. Of course, you have cosmological tests, but they're much weaker than the lunar laser ranging and solar system tests. And very well-known examples of those include chameleon screening, Weinstein screening. You have more exotic ones, camouflage stuff. But these appear quite naturally in scalar tensor theories. And just to give you a glimpse of how they work, if you have, for the chameleon screening, if you have this G4 function, which I showed you, which is the effective Newton constant, then you will have, you have very naturally, if you have this kind of potential for the scalar field, then you also have a contribution from the energy density to the potential of the scalar field. And if you have this infalling potential, which is like here, I wonder if you can see my cursor, I hope so. You also have the energy density, which gives you this linear dependence on the potential. And that means, the mass of the scalar field is given by the second derivative of this effective potential. So if it's not so convex, then the mass is very low. But if the function, if the density is much higher, then this function is much more convex, and the second derivative at the minimum is larger, and then you have a high mass. And why does this matter? It matters because if you're in a high density region, such as in a galaxy, this mass that you're going to have for the force that's going to be due to the scalar field is going to be exponentially suppressed. So for example, if you look at this geodesic equation, which normally would be equal to 0, here you have this so-called fifth force, which is a Yukawa fifth force. If the mass is very large for the scalar field, then you're just going to exponentially suppress this force, and you're not going to see the effect of the scalar field. And that's why we say that you screen and you recover GR locally. That's a very rough picture, but I hope you can take something out of it. And now I want to talk a bit about gravitational wave propagation. And why is this so interesting? So before I talk about scalar tensor theories, I have to talk a bit about GR gravitational waves. And what are those? Well, those are perturbations of the metric. Here, eta mu nu is just a flat Minkowski space, and h mu nu is a small perturbation to the metric. And these are what people call, this h is what people call gravitational waves. Then, if you write the field equations and you play a bit around them, you see that you have this box operator, which is a wave operator, which acts on h, and it is sourced by matter. But it has a very weak coupling, the inverse of Planck mass squared. So you need very, very heavy objects to produce gravitational waves. For example, black holes, very large objects, they rotate around each other. They can source gravitational waves. and emit them. And if you want to see what is the effect, if you want to see what is the effect of those gravitational waves on matter, you can think you have to inspect the geodesic deviation equation, and in particular the Riemann tensor, which gives you the tidal forces. Because you can always, eliminate gravity at a specific point and go and work with Minkowski space, but not for the tidal forces, which give you the relative acceleration between two points at a finite distance. So for example, on this, if you put some particles on the boundary of this circle and you wait over time and the gravitational wave goes through the screen, as time passes by, you will have this deformation, which are called the H plus and H cross modes. So the plus, because it builds a plus like this, you can see, hop, it's the plus. And here a cross is just rotated by 45 degrees. It looks more like a cross if you would superimpose these images here. And because of the properties and the rotation of this deformation, we say that this is a spin 2 field. What does it mean? In general, for a spin S field, the field is invariant under rotation of 2 pi divided by S. So if here we have a spin 2 field, it means that it's invariant under rotation of 2 pi divided by 2. That's pi. That's 180 degrees. And that's why I think it's useful to think about the gravitational wave as a rugby ball. If you perform a rotation of this rugby ball and you forget about this line here, it looks exactly the same. That's a gravitational wave. One more thing about these gravitational waves is that, in this in-spiral phase, when the black holes are sufficiently far from each other and you can ignore sufficiently high relativistic corrections, the time frequency, there's a very clear prediction for the time frequency evolution, the evolution of the frequency with respect to time, and it's given by this so-called chirp mass, which is a combination of the masses of the two black holes. And suppose you have a network of detectors, you can measure H plus, measure H cross. You divide one by the other, these two factors, they cancel out. You can extract what is the inclination angle, which is the angle between the orbital plane of the system and the line of sight. And then once you have this inclination angle, you also have the frequency you can extract, and you have the chirp mass because you've measured the frequency. You can extract the gravitational distance, which is in the denominator, and which just is very instinctive. As the gravitational wave propagates through space-time, the amplitude is going to decay, and how much it decays depends on this gravitational distance. And in general relativity, this is just given by the luminosity distance. This is why these kind of events were called standard sirens. So here you can make the link with the title, the sirens, standard sirens, in analogy to standard candles. Standard candles, which, supernova type 1a, for which we can measure some flux. If we have some calibrated luminosity, we can extract the luminosity distance. And here, so you really get a direct measurement of the luminosity distance without any calibration. And that's very nice. Probably experimentalists disagree about this, but what you don't have access to is a redshift, a notion of redshift. There are many other ways to obtain the redshift. For example, if you have binary neutron stars which collide, they will also emit light. So you can say, hey, in this direction, there was an event, gravitational wave. I measured the luminosity distance. Since you've observed light, you observe very well where it comes from, and you can identify the host galaxy, and then you can extract the redshift. And if you do that, you can build a Hubble diagram, and that's so great because we can measure H0 and things like that. And now I want to talk about gravitational wave propagation. And this is so interesting because, is that what I want to say? Because the gravitational waves, they're produced in these screen regions where GR holds very well. So we know how to predict the waveform, but then they travel through these on-screen regions in all the rest of the universe where we can expect that modifications, they can either accumulate or just happen in this gravitational wave, they get less and stuff like this. So what can we learn really from the propagation of gravitational waves? And one example is about the speed. So in 2017, you might remember that two neutron stars, they collided. And at the moment they collide, we observed the, before we observed the gravitational waves. And when they merge, they also emitted some light. And the light arrived 1.7 seconds later than the merger of the gravitational waves. And because they've traveled over 40 megaparsecs, which is such a large distance, we can put some very tight constraints on the speed of a gravitational wave. And that's very useful because it allows us to eliminate all the terms which predict that the speed of a gravitational wave is different from the speed of light. And you see many, many terms drop out. And that's so great because it makes really my life easier because I have only this simplified theory to study. So well, it's not a theory, it's a crew of theories. You still have quintessence, K-essence, of course, the cosmological constant. You still have kinetic gravity braiding. This term is also necessary for Weinstein screening. You still have this conformal coupling, Brzezinski, the chameleon, cubic chameleon. Yes, and so when I arrived, I forgot to put my chronometer. I think it's fine. So when I arrived in to start my PhD, people were doing studying the propagation of gravitational waves in a homogeneous universe, such as this very homogeneous thing here. I put just homogeneous color to show you what it looks like. And in this Friedmann-Lemaitre-Robertson universe, well, you have second derivative with respect to the kinetic term. You have a friction term, the Hubble friction term, which tells you that the gravitational wave decay is the inverse of the luminosity distance instead of the co-moving distance. And then you have this alpha m, which may differ from 0 for scalar tensor theories. Of course, the speed is the same. It has been constrained, so up to some caveats, we trust that it should be 1. And so if you assume screening at the source, which of course you may realize that it means that you have an inhomogeneous universe, which is not well modeled by a homogeneous background, right? If you assume that you can measure the waveform and do all the extraction I talked about, then the result for the gravitational distance is not exactly the luminosity distance. It's given by this ratio, which depends on d4 at the time of observation divided by d4 at the time of emission. And you remember this d4 is the effective Newton constant. It's just very homogeneous. So if it is so homogeneous, then it depends on the time of observation and emission. That's great. You might say, oh, I'm going to constrain the effective Newton constant over time. And people got super excited and working out what constraint we could put with Lisa. And this is, for example, a coupled Galilean with a cosmological constant. We see if we measure the gravitational distance at redshift 5, we can put some constraint on this beta parameter, and we can bring it, perhaps the best constraint we can put with Lisa is of the order of 10 to the minus 2, I think. So 0.01 here, that's the best constraint we can do. But then you have to worry a bit about screening, of course. So a guess is that maybe this is not as beautiful as you think. It depends on the observation and emission point of the average value of G4. Maybe it depends on the space-time point of observation and emission. In which case, if you assume that the source is screened so that you can observe the waveform, and it works as in GR, and you are in screening regions because you have all these tight constraints, then this has to be very close to 1. And, you should worry a bit about this. So this is really the context of my research. And I think the timing is quite right. So yeah, the questions that I ask myself are of this type. Can we probe deviations from GR? What is the gravitational distance? Is it equal to the luminosity distance? Is it not? Are there extra polarization modes? We have the plus and cross in GR. Is there something else here? Do gravitational waves decay into scalar waves? Are there polarization interactions? What about lensing? Is the polarization parallel transported? And these are, this is a bit the heart of my PhD. So it's really, I'm really trying to study why, what happens as the gravitational waves, they propagate in the curved spacetime on a trajectory which can be parameterized by some affine parameter lambda. And okay, this is the most technical slide of my talk. It's a bit the state of the art of what we reached in this paper together with Pierre and Lucas. And I'm going to walk you through it. So what we do, instead of considering metric perturbations on top of a flat Minkowski space or an FLRW universe, we consider a very generic metric, which we leave unspecified. So it can really, model astrophysics, the universe as complicated as it is, with filaments and galaxies and very weird things. It's just a small perturbation on top of this. This is what we call a gravitational wave. And then, of course, we have the scalar field. So what we're going to do is that we're going to have a background scalar field, which also models the background, which is sourced by galaxies and stars and stuff like this. And we're going to use delta phi, which is going to be a scalar wave. And what we do is that we linearize the equation of motion, and we get something very complicated, which we wrote in the most compact form here. Else, if you write down explicitly all these guys, it's probably 2 or 3 pages. But I'm just going to walk you through it. So we have these second derivatives here, which we call kinetic terms. All of these, they act on this 11-dimensional vector. So delta phi, that's the scalar wave, and h rho sigma, it contains 10 elements. So it's 10 elements here. So this is an 11 by, these are 11 by 11 matrices. And then we have second order derivatives, and then we have other terms, which we call amplitude terms, which have only one derivative acting on these delta phi and h. And then we have these mass terms, which have no derivative. And what I want you to focus on here is the off-diagonal terms, which are really mixing between the different fields, delta phi and h. So we don't like that specifically at the level of the kinetic term, because we don't really know if it's an equation motion for delta phi or for h. At the level of the amplitude, it's fine because it's just an exchange of energy between the two waves. But at the level of this kinetic term, we don't like it so much because we don't understand. So what we had to do, and this was a bit of luck, is to find, I don't have a systematic way to find this, I have to say, it was just luck, I guess. Try and fail. We found this variable, which we call gamma, which depends on the trace reverse part of h mu nu. So it's h mu nu hat, which is h mu nu minus 1/2 of g mu nu h, where h is the trace of h mu nu. And then we have this extra tensor here. And if you do that, and you impose this generalized harmonic gauge on gamma mu nu, and this you can do because it's a gauge condition which does not depend on the equation of motion. It just, you can really do it no matter what, if your background spacetime is sufficiently smooth. So you don't really have holes and stuff like this. But if you do that, you can really get rid of these two off-diagonal terms here, which annoy you. And now we really have a clear equation of motion for delta phi and a clear equation of motion for gamma. And we've disentangled the mixing at the kinetic level for these two fields. Now what we only have is interactions at the level of the amplitude, which is great. So if we want to go further, we can make a wave ansatz for these two fields, delta phi and gamma. We say that there's an amplitude part, which is the one that decays as the inverse of the distance. We don't know which one yet. And then we have the phase, which it's a wave, so it oscillates with time. And we call the phases V and W in general for the different fields. But we have this omega here, which we say it's a large parameter. And when I first read this, it was very confusing because people said at the end of the computation, we set it to 1. But the only thing it's useful for is to keep track of how many derivatives have hit in the phase. And you see, so the second order derivatives, they're going to hit the phase twice. Also, they're going to hit this guy. But if the phase varies much faster than the amplitude and the background spacetime, and this is called geometric optics, then we have this ordering between the different terms. And intuitively, you can think of this geometric optics regime where you have a gravitational wave, which has a wavelength, which is much shorter than the typical scale on which the background varies. So here I've tried to plot a background which varies slowly. And all right, so then we have this ordering between the different terms. This one is so much larger than these guys and so much larger than these guys. And then we can neglect these guys. And this is a very typical approximation called geometric optics, which makes our life so much easier because then we have just these terms, kinetic and amplitudes exchange between the different fields. But we still have these off-diagonal terms. So we may wonder if there's an exchange of energy. But before this, we look just at the dispersion relation, the order omega squared terms. And from the equations of motion for the tensor, so for the gamma, we found that the k, which was just in front, is proportional to the metric. So it's just a contraction of the wave vectors of the tensor mode, which we call k. And this tells us that gravitational waves, they propagate along null geodesics, and they propagate at light speed. This is not so surprising because this is what we fixed we started with theories which predicted that the gravitational waves propagate at light speed. And from this condition, we can deduce this condition on an evolution equation for the wave vector of the tensor modes. If we look at the dispersion relation for the scalar mode, then this k here is not proportional to the metric. There are additional terms which depend on g2xx and g3x, and which break actually the speed of propagation, which make the scalar waves propagate slower in general than tensor waves. So what we find is that the scalar mode propagates a bit slower, and there's a different evolution equation for the wave vector of the scalar mode, which is p. It depends on this gradient of u, which depends on g2xx and g3x. And we find this condition that the scalar waves, they propagate at the speed of light if g2xx is equal to 0 and g3x is equal to 0. So the general picture is that we have scalar waves which propagate slower than the tensor waves. And of course, if they don't propagate at the same speed, you may wonder how interactions may take place. But that's the next question that we ask. How does the amplitude evolve? And here, that's the equation, the order omega to the power 1 equations. So it's the evolution for the amplitudes. Here you may remember lambda is the affine parameter. If you integrate this relation, you can find out what is the amplitude of the tensor mode at the end of the geodesic, for example, having integrated out these guys. And if you forget about these blue of these phases right here, right now, you may realize something. If you start with only gravitational waves, tensor waves, you have no scalar, you're going to source the scalar wave with the tensor waves. Forget about this guy. And then once you source the scalar wave is going to back react on the tensor wave. And you may say, oh, that's so exciting. We're going to find some exchange of energy between the scalar wave and tensor waves. That's great. Does this really happen? So we study these two cases when the phases match. So V is equal to W, in which case the scalar wave propagates at the speed of light, and we have these G2xx and G3x, which are equal to 0. In this case, this is really schematic. The real wave equation evolution equation looks like this. What happens is that the interaction terms, they vanish. So the interactions are turned off. And that's so sad because there's no energy exchange between these two guys. And the second possibility is if the phases don't match. V is different from W. in which case the scalar waves, they propagate slower than the speed of light. And in this case, you can integrate, for example, for H plus, the equations, and what you find is that you have this term here, which oscillates very rapidly. You see, so you're integrating along the geodesic, something which oscillates very fast and between -1 and +1. And so you're going to have something which averages out to 0. And this we call incoherent interference. And so the conclusion is that no matter what is the speed of the scalar waves, what you have is this beautiful conservation law, which holds in an arbitrary spacetime. So you have this H plus and H cross, which decays as 1 over this notion of distance and square root of d4, where the bar indicates that it depends on the background value of the scalar field, but it could be a generic background, right? Not FLRW, it's sourced by astrophysical objects. And from this conservation law, we can conclude two things: that the gravitational distance is given by this, this ratio of d4 functions at the background value of the scalar field, which is evaluated as the space-time position of observation in source. And this is really because you have this conservation law along the geodesic. And for popular screening mechanisms, and I must insist because I'm here on the word popular, so for Weinstein screening, for example, and for the chameleon screening, these have to be really close to 1. For example, Weinstein screening, you have to satisfy the lunar laser ranging constraints, and at most this can differ by from 1 by the order of 10 to the -5. This is in Tsujikawa 2019, so that's very low. And yeah, for chameleon mechanism, it's the same as in this paper. So that's really sad. And another thing is that we can extract. So of course, there's no exchange of energy between the plus, the cross, and the scalar waves. This we have found, but we can define a notion of scalar distance. So if there is, say, a source which is not screened, which emits a gravitational waveform which contains some scalar wave, then this is how the scalar wave is going to decay. It's going to decay by 1 over ds, which depends on all these coupling functions. Of course, this may not be so interesting in itself, because if we discover scalar waves, that's enough, right? We've discovered scalar waves, and we can say, oh, that means that GR is wrong. So another consequence of this conservation law is that the polarization is parallel transported. I don't give too much details, but it depends on this. It's a consequence of this equation. And it means that there's no energy exchange between the scalar and the tensor wave, and also not between the plus and the cross polarizations. And that's, to some extent, a bit sad, because we would have liked some deviations from any of this, but it doesn't seem so. So one more thing is the polarization content of this of these gravitational waves. So we also have the plus and the cross. So you see here the plus, the cross, very exciting. And in general, the scalar wave will also give some signature in the detector. In the form, if it's propagating at the speed of light, it will give this breathing mode, which is, it looks like someone is breathing. So that's why the name. And in general, if it propagates a bit slower than the speed of gravitational waves, then it's going to arrive late, of course. And then the shape is very complicated. It depends on the gradient of the background scalar field. And here what we did is we just said it's a symmetric matrix, so we can diagonalize it, find a basis in which it's diagonal. And all the subtleties are hidden in these 3 numbers, C1, C2, and C3. So very exciting. We have this extra scalar mode. And here I want to ask a very simple question. Gravitational wave extra polarization modes are a smoking gun signature of beyond GR physics. This is not a question. The question is this: really? Is it really a smoking gun signature of beyond GR physics? So we've seen in this Horndeski theory there's this extra scalar mode. And here I want to ask the question, is there also maybe other extra polarizations in GR? And so that's the second part of my talk. I guess I have enough time. Yes. So if you write down the curved spacetime equation of motion in GR, so there's no scalar field. Here is just plain GR, the field equations. In a curved background spacetime, what you find is that you still have this wave operator here, which are second derivatives acting on the metric, but you also have an effective mass-like term, which depends on the Riemann, actually on the tidal forces. And this is a mass-like term, so it's something that we've neglected following the geometric optics approximation early on. So we said, yeah, you know, if the background is sufficiently weakly curved, then we can neglect these terms. But this is not necessarily always true, and specifically also with LISA and with pulsar timing array, we're also looking at very, very long gravitational waves of the order of the astronomical unit, so they can become really large. And the question we want to ask is that, are extra GR polarization modes excited by the strong curvature near a black hole? So here, there's a black hole, there's a gravitational wave emitting gravitational wave source here. The gravitational wave gets lensed, it hits in the lens plane with an impact parameter B, and then it gets detected in VMO. And here we want to ask, you know, here you have some very strong Riemann tensor. Perhaps this gives a mass, and you know, massive gravitons, they can have extra polarizations. So, okay, that's the second most technical slide of my talk. What we want to do is to absorb the effect of this Riemann tensor and the amplitude of the gravitational wave. And so to do so, we still have this large omega, but we want to take into account corrections to the amplitude with this omega to the power -1. And this omega 0 is just what we've calculated earlier. You may remember this, this equation of motion what we found. So we had this null geodesic part, which was omega squared, the dispersion relation. Then we had the omega to the power 1, which was an evolution equation for the amplitude tensor. And the second line, sorry, is the order omega 0 is always neglected. People just neglect this. They say it's geometric optics. This is small, trust it, don't question it. And of course, we are very curious, so we want to question it. And so since we have this epsilon mu 1, we can absorb the effect of the Riemann tensor in the evolution of this correction to the amplitude. And to do this, I realize this is a bit complicated to grasp in such a small slide, is that we make an expansion for the polarization tensor in terms of an amplitude, and we expand this guy on a local tetrad basis. So it's a basis, actually it's a set of 4 vectors which, you know, span the tangent space of the tangent space at every point of the geodesic, and it depends on this k mu, which is the wave vector, and also some other vectors. And M and L, they're, for example, perpendicular to K, and we expand this guy on this basis, all symmetric combinations of this guy. So we have 10 of them, and then we want to see for which ones we get a result which depends on this, which was sourced by this Riemann. And if we make this ansatz for a point-like length, for example, you consider a black hole, but you're still sufficiently far that you can linearize in this guy psi or the Schwarzschild radius if you want. We can solve for these theta's, which I've just shown you in skipping an enormous amount of steps. And what we find is that there is the value of the source. It decays as, of course, 1 over the distance. This is the luminosity distance, but we're in Minkowski space, so it's the same as the co-moving distance. And then we have these source terms, of course, which depend on the Riemann. And this Riemann, if you go very close to the black hole, this is the lens plane. If you hit the lens plane with this impact parameter B, your H plus and cross polarizations are fixed, perhaps this guy is not going to be 0. So I still have a bit of time. So what we find performing all these integrals is that there are 2 extra modes, scalar modes actually. There's an extra breathing mode, which is this guy, and which may remind you of some Horndeski theory, where I told you there's this guy in Horndeski theory. And there's this extra longitudinal scalar mode, which is here there's just the axes are changed. There's the z-axis to the right, and this is the xy plane. And so this is what people call a longitudinal because it's in the direction of propagation of the gravitational waves, which always propagate in the z direction. And we calculated the amplitude of these guys by performing all these integrals. And we found that they scale as the Schwarzschild radius times lambda divided by b squared. So if you go really close to the black hole, this b is small, it cannot be too small because we've made some assumptions. But for large gravitational wavelengths, for example, LISA or pulsar timing array, perhaps this correction can still be quite significant. And I'm not sure I have time. How much time do I have here?
Yeah, you can have another 5 minutes or so.
Yeah, okay, that's fine. So, so for what people typically do when they study lensing of gravitational waves is that they have an amplification factor, which relates the situation in which there is no lens with when there is a lens. And this is just you're summing up all the different paths. The source does not emit just the gravitational wave in this direction. It emits in all directions. And then you have to integrate over all the different paths that the gravitational wave can take. And if you're located in some special region, then your signal is going to be amplified a little bit. And what we claim here is that, in fact, this is a bit insufficient for very long gravitational wavelengths, is that you have to introduce also on top of this polarization distortion tensor, which is this rank 4 tensor, and which allows you to have these distortions of the polarization tensor. So it's not that you start with fancy polarization, is that you start with plus and cross, you propagate close to the black hole, and then the black hole excites these scalar modes, and you've distorted the polarization of your gravitational wave. And of course, then you may wonder, but you see this correction, nobody cared about why, maybe they're so small. And what we did is to wonder, is this very likely? Is it likely that we develop these scalar modes in GR? And so you can ask the question, what is the probability to create a scalar mode which is mu power minus 1 times smaller than the tensor mode? So for example, mu is 1 divided by 100, and that means that the scalar mode is 100 times smaller than the tensor mode. And we can compute this probability if the source is at redshift ZS, and the cross section is given by this, this B max, which gives you a surface on the sphere. And then it depends also on the number of lenses that you have. And this depends on what kind of lens you're considering. But here we've considered galactic lenses, and quite a realistic one. And we also took the largest possible wavelength to maximize the effect. And this is for the pulsar timing array. So I think 5 parsec of wavelength. And for a signal which is 10 to the power minus 4 times, so 10,000 times smaller than the tensor modes, you see this blue curve here. So as you reach redshift 5, say, you would need roughly a million sources to see with probability nearly one event with a scalar mode, which is 10,000 times smaller than the tensor mode. So it's not so likely, but as we will get more precise with detectors, perhaps one day we will detect one event, and at this point we have to wonder, well, was this a GR event, or was this really a smoking gun detection of gravity beyond GR? So finally, perhaps I can skip this. We can answer if you have any questions at the end. It's just to check that our result does not depend on the observer, and we had to check that if we perform some Lorentz transformations, we cannot get rid of these scalar waves, scalar modes, and in fact we cannot. We can transform some of the scalar to some vector mode, but we cannot get rid of the extra polarization modes. So now it's time for my conclusions. So I'm just going to go through them. So the only difference for the tensor modes with respect to GR is on the distance. So this holds even in the presence of lensing, traveling through screening regions. If you have peculiar velocities of source and observer, it's actually a consequence of graviton number. Have not discussed this, but that means that you have this relation and it holds in all of these cases. So that's great because the luminosity distance, it has been calculated for light in many different spacetimes, for example, in a perturbed FLRW, and you can use really these results for this gravitational distance. Second thing is that you have an extra scalar mode, which may be detectable even in presence of screening, well, as long as the geometric optics approximation holds. And that might be the most promising way to go forward in detecting deviations from DR. But it needs to be produced at the source. And that's not happening if screening works very well. Within geometric optics, the polarization is parallel transported and there is no polarization transfer between the different modes. And finally, beyond geometric optics corrections, they also lead to the scalar breathing and longitudinal modes for less gravitational waves. However, the probability to do so is very small. And I think that's it. So I will stop here and thank you very much. And I'm open to questions.